Thank you, Mr. Christian Nti, for this opportunity. You rightly said last week we had a presentation on the Ashaiman and Iture bridges case study. And the need for the second part had arisen because of some feedback that we got from participants. In the first part of the presentation, under the above theme, the theme we just mentioned, the following topics have been dealt with. That's the importance of bridge maintenance, some important bridge news, inspection of bridges, types of cracks in beams, types of maintenance intervention, common defects in concrete bridges, deterioration mechanisms, extending bridge service life, and we talk about structural strengthening, Iture bridge study, and Ashaiman overhead repairs and strengthening. Then after that, we gave recommendations to GHA as to how to enhance our bridge design, construction, supervision, and maintenance of our bridges. And we had some feedback from the participants after the presentation. It was made known to me that the topics that we have, there are some topics that have not been well explained due to the time constraints and the need for us to come back and highlight on those topics. That is deterioration mechanism, under which we spoke about creep and shrinkage, carbonation, corrosion, alkali silica reaction. These were reactions that we got from the participants. So we've taken we want to take the opportunity today to talk about these few items that have not been well explained. First, the creep and shrinkage that we talk about as one of the mechanisms that concrete defects are seen when those mechanisms happen within the concrete. So creep and shrinkage is one of them, which are two time-dependent phenomena that affects the behavior of reinforced concrete structure. Creep and shrinkage, they are time-dependent. And throughout the course of time, structural concretes may undergo wear and tear, which may cause cracking, stresses, or deflections that will affect the in-service behavior of the reinforced concrete structures. This phenomenon is a creep and shrinkage. And the effects of this phenomenon on concrete members include cracking, loss of pre-stress, bond issues, leakage, and durability. That is when creep and shrinkage are experienced by the concrete member. These four things are observed in the concrete members. So by cracking, and the cracking that we're talking about, we have, as concrete shrinks, it exerts tensile force on itself. Concrete, as we know, is very weak in tension. And whenever there is tensile force within concrete, then that is very dangerous to concrete. And shrinkage induces tensile stress in the concrete. If these forces exceed the tensile strength of the material, which is very little compared to the compressive stress, then we see that cracks develop. These cracks may be seen to be fine cracks or deep cracks. All this will have happened due to shrinkage in concrete. And the loss of pre-stress concrete. We have cases where when we have this in a pre-stressed concrete, we have steel tendons that are pre-tension or post-tension. That is when we talk of pre-stress. We have in the fresh concrete reinforcement steel tendons which have been stressed, concrete cast. Then there is a bond reaction between the concrete and the tendons that makes the stress potential or stress carrying capacity of the member to be very high. But when there is shrinkage, it affects the load carrying capacity and behavior of the structure. And the next is the bond issues also within concrete. Whenever there is shrinkage-induced cracks, it weakens the bond between concrete and reinforcing steel bars. When there is concrete and reinforcement steel, and the bond between them gets weak, then the effects of the reinforcement bars will be reduced or even getting 10 to 0 when there's complete loss in the bond. So this will compromise the structural integrity and durability of reinforced concrete member. All these things happen due to the shrinkage that comes into the concrete. And also leakage and durability are one of the effects of the shrinkage in the concrete. Shrinkage cracks provide pathways for moisture ingress. Water and aggressive chemicals can penetrate through these cracks, leading to corrosion of rebars and reduce durability. So these are other things that happen to the concrete members when there is shrinkage and in the concrete. So when we have such a case, what is the solution? We have the concrete, it experiences shrinkage. To mitigate these effects, we use techniques such as these techniques that we're talking about are techniques that are considered during construction and considered in the design and also during construction. When those things are followed, then the shrinkage effects would be mitigated. One of such techniques is control joints. Control joints are different from expansion joints. Within concrete, when we are casting a very massive concrete, a very wide or big, wide area concrete, like a big slab of a deck, and during this casting, we create cracks. We create cracks during the hardening process of the concrete, before the concrete get fully hardened, and also the concrete not in the very soft stage. When it is semi-solid, we create cracks in the concrete, and this crack will be created on a particular line so that whenever there is shrinkage and there is going to cause crack, the cracks will be absorbed by the induced crack, which is called the joint crack. So we shall define to the concrete, because we can't stop the crack from happening, but we can define the direction of the crack so that it can easily be repaired as and when it happens. But if control joints are not used, what happens is that we shall have a very ugly face of a concrete, cracks passing everywhere. So control joints is one important. Then second technique is proper curing. When we cast the concrete, the curing process of the concrete has to be properly done, so that concrete will not be left to the weather when there's intensive heat without controlling the amount of the heat that will be absorbed by the concrete. So proper curing will be one of them. And the third is use of shrinkage compensating admixture. Admixture, if time allows, we shall talk on admixture. These things will be put in the concrete in the liquid state, and it takes care of all potential cracks that will come due to shrinkage. Now, the second mechanism that we talked about last was carbonation. Carbonation is a process that happens within the concrete when there are some cracks that make room for atmospheric air to get into the concrete and react with the free lime in the concrete. The water, the corrosion of the reinforcements in the concrete is always protected because there is a pore water which is in the alkaline form, highly alkaline pore water. That is in the hardened cement concrete. When that water is around, it protects the reinforcement from corrosion. But when there is a way for atmospheric air, carbon dioxide to come into the concrete, then it reacts with the free lime, and this reaction is what is termed carbonation. And when the reaction continues, then it reaches to the reinforcement. What happens is that corrosion will occur in moist environments. So the reaction of carbon dioxide with the free lime causes any moist that comes in will cause corrosion. And there is to protect this, as we said last week, is first to have a proper cover of reinforcement. For every structural member, there is a stipulated cover, depending on the exposure condition that the concrete is going to have. With that exposure, the code will tell us what concrete we should use for particular exposure. If the concrete is going to be exposed to a very an environment where there is a chemical attack, maybe from the sea or from the soil, or when there is anything that is possible to happen on the concrete, exposure to the concrete. So there will be a stipulated cover. If those things are followed and achieved, then corrosion will not even happen when carbonation comes in. So the exposure classes, as we're talking about, we have, for purpose of design and certification, the environment to which concrete will be exposed during its entire life is classified into various levels of severity. Like in British codes, we have, in many years, the exposure conditions we use were mild exposure, moderate exposure, severe, very severe, and most severe. These were what we've been using in the British code. But in the change in BSCN 261 and BS 85001 and EC2, the conditions are now classified in terms of exposure to particular actions, which with various levels of severity. For instance, we have categories like no risk of corrosion attack, then they will know what concrete cover we should use and what kind of concrete water cement ratio we should consider, and so on and so forth. So the exposure considered are these, as I mentioned: corrosion to attack, corrosion induced by carbonation, corrosion induced by chlorides other than from seawater, corrosion induced by chlorides from seawater and freeze-thaw attack, and chemical attack. So this, from these exposure classes, we have this table that will show us whenever we are designing or whenever we're going to construct, we look at this chart and know with whatever exposure classes we are talking about, we shall see what concrete class we should use, what concrete cover we should have, and what water cement ratio we should be considering. So when these things are followed, then those reactions like carbonation will not have much effect on the concrete. And the chemical attack also, as Portland cement concrete is liable to attack by acids. Concrete made with Portland cement is not recommended for use in the acidic conditions where pH value is 5.5 or less. I mean, when you use ordinary Portland cement concrete, wherever there's going to be exposure to acidic condition where pH value is 5.5 or less, then when we are going to do concrete there must be a thorough care or consideration of the exposure condition and the intended construction. The most common form of chemical attack that concrete have to resist is the effect of solutions of sulfate present in some soils and groundwater. Some soils or groundwater, when they have sulfates in them, they can have serious effects on foundations. They can have serious effects on our substructure like the abutments, which will have backfill, and it will have serious effects on our pH, which is founded in the soil. So a presence of sulfates can be very dangerous to the concrete. And concrete resistant to chemical attack is related to free water ratio, as we said. The amount of water that we have, the excess water after this in hydration, after the concrete has hardened, the excess water that is in the concrete creates some pores. That is the free water create some pores which will cause effects on the concrete. So these are things that we mentioned. Alkali silica reaction was well explained last week as one of the mechanisms. So now the whole thing is issues to do with water and concrete. All the undesirable phenomena described above have resulted from the presence of water in concrete, and we can't avoid water in concrete. So what do we do? Now, what's the solution? Making concrete resistant to water penetration. That is the solution. And how do we do that? We have many options, but generally two types. One option is the external coatings using membranes and impregnation. When we have like an abutment, when we have like a retaining wall, which are exposed to soil that has so much water in them, that have so much water in them, they will have effects. They will have effects on the member, like the wall or the abutment. So one option of protecting this is to have external coatings that will be applied on the wall, or applying some membranes, or impregnating the walls with some gouts or some admixtures that will not admixture after the wall has been cast, is even functioning. When these things are observed, the three things that can be done on them are the coatings, membranes, and impregnation. And this has no change to concrete microstructure. The concrete is intact as it is. It will not have any effect on the microstructure of the concrete, and it can be done repeatedly. When there's a problem, material can be removed, and the coating can be done, or membrane can be applied. But it needs time. It requires time, and it's very expensive compared to the second option that we are going to talk about. So waterproofing example, we have the wall and the back outside of the structure. These are the things that will be done to protect the wall. Just like we have this wall, from inside, the effect of water is observed, and the only thing that can be done here was to remove the material abutting the area that's affected, and coating will be applied, as you can see on the picture. So the second option, which is internal or integral, that is using admixtures. This is easy to use, but it's also inexpensive, but we have less control over outcome, meaning you are to cast an abutment, you are to cast a wall, then you put admixture in the concrete, and the material, the admixture, are very cheap compared to if we should use membrane or the other things that are mentioned. And also, but the only disadvantage of it is we don't have control over the outcome. Some things will go wrong during the mix without us knowing, and the effects of the admixture may not be observed in the life of the concrete. So the waterproofing admixtures that are always used, we have two types: hydrophobic crystalline admixture and hydrophobic pore sealing admixture. The admixtures are the first one, which is the hydrophobic crystalline admixture, they modify the concrete mixture, and also they have some potential to reduce water absorption and permeability. When those things are used, the concrete will not absorb water, and the concrete will not be permeable by water. And it serves like a raincoat for the concrete member, although it will be raining, but the concrete will be still dry. That is the hydrophobic crystalline admixture. Then we have the hydrophobic soil sealing admixture. That one is also hydrophobic, but the difference is that this admixture creates barrier against water by blocking the pores and capillaries in the concrete. That's the one. The second one pores and capillaries in the concrete are blocked, while the first one, it has effects on the concrete microstructure. And when the recommended techniques are not used during the construction, crack starts appearing during the structural service. Like what do? We do injections for sealing or bonding or filling. This depends on the characteristics of the concrete. Whenever we have concrete cracks, we see the crack type, the path of the crack, the width of the crack, the movement of the crack, the reason for the crack, and the condition under which the crack has come, and the previous measure that has been taken. This will determine whether the injections are going to be for sealing or for bonding or for filling. Example, we have here cracks characteristics. You can see different types of cracks, some along the line of the reinforcement, which shows that there is a problem of bonding that creates that crack. We have the one also under the surface crack. We see some cracks. This could just be due to high temperature or due to shrinkage, which has got nothing to do with the reinforcement. So that one will also have a weight. And the other two separating cracks, these are structural. We can see that, like the one we showed the last time, we are showing a bending crack and we are seeing shear crack. So these cracks will determine what kind of injections to be done. So for the injections, we should know what do we use where. We have types of injections. Epoxy is one, flex PU resin is another, and water stop PU foam is another. When it is a structural crack, then we use epoxy because it's not only to fill the crack, but also to enhance the structural capacity of whatever crack has come. And when it is a leaking crack, it doesn't have any structural implication, so flexi PU resin will be used. And when we have uncontrolled water inflow due to some cracks, then we use water stop PU foam. So these are things that happen. Now, when we have, these are the cases that we shall have in the life of our concrete. Now, we have a question to end this presentation with. Very important to answer. With the current state of our water bodies, where small-scale mining has polluted the rivers, my question now is, can we guarantee the water and soil around our bridges to be free from chemicals like chlorides and sulfates? Can that be guaranteed? Do we think the exposure condition considered, if any, during design and construction is what the bridges are being exposed to today? Do we expect our bridges to meet their expected lifespan? What then should we do as a country to mitigate any possible disaster? We said in the previous presentation, and we repeated in today's presentation, that the environment around our bridge structures, especially the substructure, they are not friendly at all. Most of the old bridges we have, we can't even guarantee if the required concrete cover, the required water cement ratio have been considered, taking into consideration the condition that our bridges are being exposed to today. So I would like to put this to the participants for suggestions to come as to how we protect our already aged bridges and the new coming bridges. What capacity do we have also as an agency to monitor the construction and to ensure that the right additives, the right admixtures, and the right concrete class and cover are achieved during construction? We thank you for this opportunity, and we hope we shall have suggestions from the participants. Thank you, and thank you very much.